Very much, Hilary. It's a great pleasure to be here and talk about the influence of Joe and my experimental work that I have done over a number of years. And this work that I'm going to talk about was very much influenced by a paper that Alan discussed yesterday. This Siam paper here.
Flapper T with a T.
Pardon?
It should be a flapper T.
Oh, sorry, you're right. Joe would never have made that comment. But anyway, it's a typo on my phone. So it's very much about that, how the rings buckle when they come under compression. And Joe's work was very much about, theoretical work was very much about a ring in free space under axisymmetric compression, and there you get a series of instabilities. In particular, he was interested in when these two sides came together. In that picture on the left was his particular interest, but you got other kinds of instabilities, other types of bifurcations where the ring will buckle into this trefoil, for example, as the next one up. So our work was very much influenced by this. But before I go on, I want to just say a few words about Joe and his influence on me. I first met Joe in 1983 when I visited John Maddox in Stanford, and then Joe subsequently came to Oxford as on sabbatical for a year in the mid-80s, I think about 86 or something, and he used to come to my lab a number of times. My lab at that time in physics in Oxford was about the size of this area up here. It was a very small lab, and I had a couple of students and myself in there. We were all doing experiments in a small lab, and Joe used to come and join us for cups of tea and discussions with me and my students and so on. And though I never did any experiments for or with Joe, he certainly came up with some ideas about some experiments I might do in this lab, and one of them was involving the stability of water jets, which he suggested we could fire from one end of the lab to the other and look at how high we could make this jet go before it started to break up. My students were not very keen on this idea of this experiment of water jets flying over their heads, but Joe used to say, well, how can you possibly have a good quality fluid dynamics lab without a bit of water on the floor? So I never knew whether he was tongue-in-cheek with this comment or not, but it certainly made us smile at the time. But my fondest memories of Joe, and this was mentioned several times yesterday, I think because of the effect it had on all of us who go there, is to Woods Hole. I've been there a number of times over the last 25 years or so, just to give, I used to sometimes just drop by to give a talk or something like that, or visiting somewhere else, or sometimes I just went there for a week or something. I never was an official part of the program, but I really, it's a magical place, and it's a wonderful place to go and give a talk. It's a really electric atmosphere, and it's really magical, and I really had the best times of my life in fluid mechanics were there in that room in Wolf's Cottage. It's a wonderful place. And I used to really, really enjoy giving talks. I'm never sure where the audience enjoyed my talks, but I used to really enjoy giving these talks. And then afterwards, sometimes afterwards, Joe would sit me down on that veranda or under the tree opposite, because it was invariably sunny time there, and he would say to me, Tom, he said, that was really interesting, but he said, you know, you said X. He said, I think you didn't really mean that. I think what you meant was Y. And then he would explain to me, you know, how I should really have understood my results and how I should, and then he would then we would go off in another direction, and it really was wonderful. It was, I consider it to be, he did this very much in private, and it was very much supportive, and he was encouraging, and he always wanted to encourage me to do things. He didn't make a big show and fuss about this in front of the audience or anything like that. We did it in private, and I really, really appreciated this help that he gave me then and over the years of my work. So the question I have is, how do you then put axisymmetric compression onto a ring, onto an elastic ring? So the way that I decided to do it, which is not quite the way that one might think about it theoretically, is supposing you take an ordinary glass funnel from the laboratory and you fill it with water, and then you put a little rubber ring about 1 millimeter or so, maybe a couple of millimeters in diameter, and it floats on the surface. The ring is heavier than the water, but surface tension keeps it, as we heard from Dominic yesterday, surface tension keeps it floating on the surface. And then what you do is you open up the tap at the bottom and you let the water drip, drip, drip out of the funnel, and so the ring becomes more and more constrained by the sides of the funnel. That was my idea. And so if I then show you a video of what happens, so there's looking down on the top, so there's a latex ring sitting on the surface of the water, and I'm going to let the water out drip by drip. This video is actually made from a sequence of still images which are put together, and as the ring goes down the funnel, so it becomes more and more confined and more compressed, and then it buckles and goes into this nice shape as it goes down the funnel. And so this was kind of my analogy with the paper I referred to at the beginning with the typo in it. But the thing is, this turned out to be a problem that was looked very much in the 1960s of confined rings or constrained rings by Chan and McMinn. They were interested in metal rings inside concrete holders inside nuclear reactors. And what Chan and McMinn managed to show that this is not an instability. It was a very controversial topic in the mid 50 years ago. It is not an instability. It's not a sequences of bifurcations that happen in this problem. You actually need to put an imperfection into the system in order to generate this buckling in this particular configuration with a constraint on the outside of a rigid outside wall and a elastic thing in the middle. And the graph over there are results of Andrew's calculations of this is the surface area of the fluid that's holding up the ring, and this is the surface area inside the ring on that level there. And you can see that there's great agreement between the Andrew's numerics and my experiments there. There's really very good agreement considering the details of the experiment, but this does not occur as a result of an instability. You have to put an imperfection into the numerics to generate this new solution, and you need to add a finite perturbation in order to get there. And so there's no bifurcation present in that problem. And as you make ring thinner and thinner and thinner, so the buckle state asymptotically approaches the trivial state of the circular ring, but it never actually gets there. And the way that one models this is a competition between the bending and stretching of the ring and an external load, and the external load comes from the confinement at the walls, and the way that Andrew did this is using a penalty method. So as the ring gets closer and closer to the wall, of course it's not allowed to touch the wall, but there's a normal reaction force that comes from the presence of the nearby wall. And in the experiment, it's held away from the wall by the action of meniscus. It gets very close to the wall, and in fact, if you're not too careful in the way you do the experiment, it gets stuck in the wall and so on. But someone needs to be careful. They're not particularly nice experiments to do. And Andrew did all these calculations using the bespoke software Umplid that they developed, him and Matthias Heil developed at Manchester. Now here's the interesting thing that comes up, that the buckling of a ring in a circular domain is not an example, is not a bifurcation. But we began to wonder whether, if we change the symmetry of the problem from having circular symmetry, if we change it to discrete symmetry, so if you started using square funnels or triangular funnels or pentagonal funnels, or we went up to octagonal funnels in the experiment, would this then regenerate the bifurcation? Because essentially we're putting in a bifurcation. Or another way of thinking about it is we've got lots of little Euler struts around the straight parts of the edge of the funnel. And so we had typical equilibrium states that we can calculate for this, are all these various states. It adopts the symmetry essentially of the domain in which it is held. So these are an example in a triangular, square, and a pentagonal funnel. You get these various shapes. And so here we have an example in the square funnel where we have two different types of states that come. One is this one that retains the symmetry of the, has the symmetry of the square on the left-hand side there, and this is a comparison between experiments and numerics. But now this new state arises as a result of a bifurcation. In fact, it's a transcritical bifurcation that gives rise to this. There are other states present, such these red ones here are the single-sided state which bifurcates over there, and you see the agreement between the experiments and the numerics is not so good there. And one of the reasons it's not so good is that when you go into these states here, it tends to go out of the plane. It tends to go back and forth at the plane. But the important point here is that these new states arise as a result of bifurcations that we were hoping for in the very first to follow up the work on the free rings. So changing the geometry of the outer container gives rise to a bifurcation. So that was the message that I want to get across to you, is that the continuous symmetry does not give you a bifurcation, but if you use discrete symmetry, it will give you a bifurcation. So that is essentially the main point of my talk, and I want to get you back on time for coffee and so on, because I know that people will move their feet and so on if I get too far on. But so we've got good agreement between, and I've done this work, or I did this work a number of years ago actually, and never published anything on it because we're really unhappy about some aspects of it. It's only recently that Andrew Hazel has managed to sort out some of these things, and an article on this will appear in a special issue of Phil Trans, which is edited by Pascali and Dominic Vella, which will appear next month in Phil Trans. There are many more things to be done with this problem, which I'm not going to do, and there's many other people who are welcome to have a go at this, because there are lots of really other interesting states here, yin-yang states and all sorts of things with different geometries and so on, and you can and there are things that break the symmetry which we haven't explored and so on and so forth. But that's my story. Thank you very much for your attention.
Tom, in the original paper by Flaherty and Co. and Joe, one of the main shapes that they were looking at was indeed compression of a circle by changing the internal versus external pressure, and in a real elastic medium, the first if there is a bifurcation, and the first bifurcation is to something which first of all takes roughly elliptical shape and then is compressed, and then you get opposite side contact, and there's interesting similarity solutions for the lobes after that happens. So I mean, the presence of the actual bifurcations is surely very important in many such things. I mean, possibly your experimental way of doing it leads to somewhat, it's a slightly more singular part of the space than the natural one in a tube, for example.
Well, I don't see why it's singular, because there are many examples of, say, for example, polymer rings inside another rigid medium. There are the example I gave of a metal ring inside a concrete. There are many other examples of this. I'm not saying it's the same problem as was studied by Joe and his collaborators, but there are many examples where this is more pertinent than the thing that you're talking about. But the thing that you're describing actually comes very close to what happens if, supposing you take a long rectangular domain and put a rubber ring inside that, and then take the water out of that. Then you get the very nice shapes that of these cases where the two sides come flattened and you get these two little lobes at the end of each side. So you can essentially mimic and get a bifurcation in that problem. It's not the same problem, of course, as a free ring, but you do get the same kind of thing where the two sides can come together and you can get these really nice shapes that look just exactly like the ones that are in Joe's paper. So I find this kind of, I mean, numerically repeated their work, and we get perfect agreement with what they did, of course. But this just seems to me, rather than, I wouldn't describe it as a singular case, I think this is an extension to the sort of thing they do, and many natural things have a boundary of some sort round about them. And so I think that this, tells you something in a different way about what is going on.
John?
I was going to insert my answer to that question, actually. I think the loadings are far from clear that it's the same. If you have the flaherty, the pressure loading, when the thing's circular, that's going to be the same as it sitting in a funnel. But as soon as it deviates from circular, it's completely different loadings.
Well,
so there's no question why you should have the same.
You've said the right thing, and I was much more vague, but that was
I mean, it could just be completely different problem.
The loading.
Yeah. But I have a question. So if you cut these rings, are they straight or are they already curved?
No, if you cut these, they will retain a small amount of curvature, of course, if you cut them. But for example, the one that I showed the video there of, you'll see a little blob on it because I actually started as a straight. When I made them, these things initially, I made them in glass tubes and then broke the glass tubes, so they started life straight. And then I bent them, and if you did that, they'll go back to being straight, those ones. But the way I do it nowadays is I've made but the workshop made for me a very nice stainless steel mold where I can inject things and it will settle. You inject these things as a liquid and then they solidify. And then in that case you'll get a ring and it will always maintain its ring shape to some degree.
That's yet another completely different problem, right?
Okay,
yeah, absolutely.
Now, can we continue this outside?
Okay, thank you very much.
Thank you very much.